Many of the artificial intelligence models that companies deploy today are, in a rather peculiar way, frozen in time. They are trained extensively in a laboratory environment, a process that can consume vast amounts of computational power and financial resources. Once this training is complete, they are sent out into the world armed with a fixed set of knowledge. They can answer questions, generate text, and perform tasks, but only based on the data they have already seen. When the world moves on, as it invariably does, the model is left behind, a digital photograph in an age of streaming video. This forces organizations into a costly and disruptive cycle of retraining from scratch, which not only incurs significant expense, but also interrupts established workflows and business continuity. This predicament is becoming increasingly urgent due to three powerful, converging trends. Firstly, the sheer cost of training these enormous models is skyrocketing. The resources required are astronomical, placing a heavy financial burden on any enterprise wishing to stay at the cutting edge. Secondly, the pace of change in our world has accelerated dramatically. Regulations shift, markets fluctuate, and new information emerges daily, rendering a model's knowledge obsolete faster than ever before. Thirdly, user expectations have evolved. People now demand and anticipate systems that are not static but dynamic, systems that can learn from their interactions and adapt to new information in near real time. At its core, nested learning introduces the idea of a temporal hierarchy within the model itself. Imagine it not as a single, solid library, but as a series of interconnected reading rooms, each with its own rules for acquiring and storing books. There is a fast memory layer, akin to a notepad on your desk, that captures immediate context, the last few sentences in a conversation. This layer is highly volatile and updates constantly, allowing the model to maintain coherence in real-time interactions. It remembers you just asked about the weather in London, so it doesn't jarringly switch topics. This keeps the model fluid and responsive from one moment to the next. Beneath this immediate layer lies a medium memory. This tier operates on a timescale of hours, days, weeks. It consolidates recent recurring patterns and facts. Think of it as a weekly journal where you note significant events, new names you've learned, emerging trends you observe. For an AI, that could be a new product launch, a shift in market sentiment, or a customer's evolving preferences. This layer is the crucial bridge preventing short-term insights from being instantly forgotten while they wait to become permanent. It learns from daily data feeds and user feedback without requiring a disruptive retraining event. The first major innovation enabling this new paradigm is the concept of deep optimizers. Traditionally, optimizers are seen as mathematical tools used during training to adjust weights and minimize errors. In nested learning, they are reimagined as memory devices. Making the optimizer deeper, giving it parameters and memory, lets it learn the patterns of learning. It records past updates and makes smarter adjustments over time. For example, a financial services firm used a deep optimizer on new market reports. The optimizer learned recurring patterns in evolving financial language. Result: adapted to new terminology faster with less data, fine-tuning costs down 40%. The second pillar is self-modifying sequence models. These systems learn how to alter their own internal workings in response to new data. They can update the rules by which they learn, not just their knowledge. Case: an e-commerce platform used one to generate product descriptions. When new slang trended on social media, the model adjusted its update mechanism to detect such shifts. Result: far less human oversight and consistently fresh language. The third idea is the continuum memory system. It replaces a rigid short-term versus long-term split with chained memory caches. Each cache has a different decay and update frequency. Fast cache holds data for seconds. Medium cache holds data for minutes. Slow cache holds longer, down to permanent weights. Visual: 3 interconnected gears labeled fast, medium, slow, all turning together. How, then, does an organization begin to adopt the principles of nested learning? The process should be methodical and incremental. The first step is a temporal analysis of your business domain. Identify the timescales at which information changes. What changes by the second, like stock prices or sensor readings? What changes daily, like news headlines or inventory levels? And what changes monthly or quarterly, strategic priorities or regulatory guidelines? That mapping informs the architecture of your multi-tiered memory system. Ensure each layer matches a real-world cadence of change. Next, select one well-defined pilot project. Don't attempt to convert all your AI systems at once. Example, a customer service chatbot that handles a specific query type. Example, a recommendation engine for a niche product category. Start with a two-tier system, a static base model, slow memory, plus a fast updating cache for recent interactions. Fast memory. This lets you build infrastructure and skills in a controlled environment. The infrastructure must support multi-speed updates. This may mean separate version control systems and checkpointing schedules for each memory tier. Developing the right team skills is equally important. The cumulative benefits of embracing nested learning are clear and compelling. The most immediate advantage is a significant reduction in the operational costs associated with retraining. Smaller adjustments, more frequent adjustments, targeted adjustments. Companies can maintain model freshness for a fraction of the compute budget. Models can acquire new skills and knowledge much more rapidly, closing the gap between an event occurring in the real world and the AI being able to reason about it. The hierarchical structure inherently mitigates the risk of catastrophic forgetting. The stable, slow memory core acts as an anchor, preserving foundational knowledge. To begin this journey, an organization should take 3 clear and manageable next steps. First, identify one promising pilot project where information timeliness is a known pain point. Do not try to boil the ocean. A small, focused success will build momentum and provide invaluable lessons. Second, assemble a small, cross-functional team and empower them to build a simple proof of concept. Start perhaps with just a 2-tier memory architecture. This team should include not just ML engineers, but also domain experts who understand the data's natural life cycle. Third, define success metrics from the outset. Accuracy, update costs, speed of adaptation, user satisfaction.